Hello everyone, welcome. My name is Lena and today I'm going to be talking about indium oxide and doping. So what is indium oxide? Indium oxide can be found in amorphous and crystalline forms. The amorphous form is a pale yellow powder as seen on the slide, and this powder, when exposed to high temperatures, turns into the crystalline form. It is insoluble in water, but the amorphous form does dissolve readily in mineral acids. Indium oxide is an N-type semiconductor with a band gap of around 3 eV at room temperatures. It's stable at high temperature and resistant to oxidation, and can be used in applications such as alkaline batteries to suppress gas formation, high current electrical switches and contacts as an anti-arcing additive, transparent conductive coatings. Okay, crystal structure. Indium oxide crystallizes in the cubic bixelite structure, characterized by a defective fluorite-type lattice with systematic oxygen vacancies. In this structure, each indium atom is octahedrally coordinated by 6 oxygen atoms, maintaining structural stability despite the presence of vacancies. And these vacancies are due to the high oxygen vacancy tolerance. The bixbyte structure accommodates oxygen vacancies without structural collapse, which is crucial for its N-type conductivity, primarily due to the oxygen vacancies that act as donor sites, providing free electrons leading into its intrinsic conductivity. Due to the symmetrical cubic structure and the low density of electron states near the conduction band, indium oxide exhibits a wide band gap of approximately 3 eV at room temperature, which contributes to its transparency in the visible spectrum. Indium oxide is a good transparent conducting oxide, also known as TCO. The cubic phase is stable at high temperatures, so making it useful in devices that do a lot of thermal cycling, so aerospace applications. Doping. So doping is the intentional introduction of impurities, called dopants, into pure materials that modify its electrical, optical, or structural properties. It's used in almost every semiconductor manufacturing today. Its tunable electrical and optical properties modify the Fermi level, mobility, and transparency. With the addition of impurities, the conductivity can wildly change. For example, let's use silicon. By adding a single phosphorus atom for every million silicon atoms, the conductivity increases 3,000 times over. But why? Silicon has 4 valence electrons, phosphorus has 5, and boron has 3. In pure silicon, each valence electron is covalently bonded to those of another silicon atom and is therefore immobile. But if we were to replace one of those silicon atoms with a phosphorus atom with 5 valence electrons, then 4 of those electrons would be covalently bonded and 1 would remain free and able to move around as a mobile negative charge. The phosphorus would then become positively charged. Now, if we instead replaced a silicon atom with a boron atom that has 3 valence electrons, then those 3 electrons would covalently bond, but there would be a vacancy or hole where the 4th electron is missing. This acts as a mobile, positively charged electron and can switch places with neighboring covalently bonded electrons, resulting in the boron being negatively charged. Dopants that add extra electrons, in this case phosphorus, are called N-type dopants because they add additional negative charges. Dopants that provide holes, in this case boron, are called P-type dopants because they add additional positive charges. For band gaps, continuing our silicon example, in pure silicon, the highest occupied energy band is full, Energy bands are made up of many energy levels that contain up to 2 electrons. Electrons cannot contribute to electrical conductivity unless they are mobile and can jump to the next unoccupied orbital or energy level. So this means that silicon's electrons would need a lot of energy to jump between full energy bands. Keep in mind that energy bands are made up of multiple energy levels. The space between these two is called the band gap. Pure silicon at room temperature has a very small amount of electrons that have enough energy to jump the band gap, and therefore its electrical conductivity is relatively low. Now, if you were to dope the silicon and have one of the atoms replaced with a phosphorus atom, then we would have an extra electron. Due to the full energy band, this extra electron would have to be moved up to the next energy band. Now, because it's in the next energy band up, it needs a relatively low amount of energy to move up to the next energy level compared to the large amount of energy it would have taken to jump the band gap. Now, if we were to instead replace a silicon atom with a boron atom, then the highest occupied energy band would be missing an electron and would have a hole in its place. This hole is able to be switched with an electron in lower energy levels, moving the electron up to higher energy levels using a lower amount of energy. Keep in mind that these energy levels are specific to atom orbitals because the energy levels are the energy required to remove an electron from its orbital, which changes depending on the nucleus. When we dope and replace a silicon atom with a phosphorus atom, we are replacing one of the silicon energy levels with a phosphorus energy level, which tends to be a little less than silicon's. So now we have a new energy level that is outside of the energy bands and in the band gap. Now this isn't much of a problem due to it only being a small amount off because it's only 1 proton off. For N-type semiconductors like indium oxide, adding an impurity like tin, the extra electron will go into the conduction band, creating a donor level, lowering the band gap and increasing conductivity. Okay, indium oxide dopants. So some common dopants for indium oxide, the N-types are tin, cerium, and titanium, and the P-types are magnesium, calcium, and nickel. The N-types are the most common and is what is typically used in industry as it works very well with the natural N-type of indium oxide. The P-type are currently being studied in various laboratories and is not used in industry at the moment. When doped with tin, indium oxide forms indium tin oxide, otherwise known as ITO, which maintains the Bix-Bite structure, making it highly conductive and even superconductive at liquid helium temperatures. ITO can be made into sheets or deposited in thin films onto glass as a transparent conductive coating that is used in plasma displays, LCD TVs, touchscreens, sensor coatings, and many more. Last distortion is minimal due to the size similarity of the dopants, like tin, with indium, which preserves the conductivity and transparency. For our tin example, it is a substitutional doping, which tin is substituted for indium and adds an extra free electron and increases the carrier concentration. So that is all I have for you guys today. Thank you so much for listening, and I hope you enjoyed it.